Hi, this is John Ainsley from Doulos. In this video I'm going to be describing Easier UVM, the big picture. Easier UVM consists of a set of coding guidelines for writing UVM code and also a code generator that generates UVM code compliant to those guidelines. In this video I'm going to focus on the big picture of UVM. That is, I'm going to describe the main components of a UVM verification environment and what they're for. And of course, the verification environment that I'm going to be describing is exactly the environment that comes out of the code generator. So the content of this video will be relevant if you're just trying to understand UVM better, or if you want to understand the top-level view provided by the Easier UVM coding guidelines, or if you want to understand the code that you get from the Easier UVM code generator. So here goes. In UVM you're going to be building a verification environment for a design under test, or DUT, that you can see here near the bottom of the slide. You're going to connect a System Verilog interface to each of the main interfaces on the DUT. And when I say an interface on a DUT, I mean something like a bus interface, or a network interface, or a serial interface, or whatever the protocol may be. So the instance of the design under test, the instances of the System Verilog interfaces, and any supporting circuitry you need in order to run the DUT, things like clock and reset generator, they're all instantiated within what we call a test harness. So a test harness is simply a System Verilog module that instantiates everything that you need to run the DUT, everything that you're going to connect it to. Then on top of that, we're going to layer the class-based UVM verification environment, otherwise known as a test bench. So in the top 2/3 of the screen here, you see a class-based environment, that's instantiating the UVM classes. And in the bottom third, we're in the module-based world, where we have a test harness instantiating the DUT. So corresponding to each interface on the DUT, we'll have an agent within our class-based UVM verification environment. The agent represents a conventional way to structure the verification environment. Each agent has a very well-defined structure. The agent consists of a sequencer, a driver, and a monitor component connected together in a predefined way. The sequencer is going to run sequences to generate transactions. So here we can see a sequence running on a sequencer, and the driver is pulling down transactions from the sequence running on the sequencer. The driver then wiggles pins in the interface connected to the design under test in order to drive stimulus into the design under test. The monitor, for its part, is also monitoring all the bit wiggling going on in the interfaces. So I'll wind back this animation and we can see it in action again. The driver drives stimulus into the DUT. The monitor monitors those same pins, assembles the pin wiggles into transactions, and then sends those transactions out to the rest of the verification environment for analysis. So the component up here labelled subscriber is analysing the outputs from the design under test. We have one agent for each of the interfaces on the design under test, so the structure that you can see here will be replicated for each of the agents. All of the agents are then instantiated within a class known as an env in UVM. The sequences running on each agent are generating the stimulus or traffic associated with that particular interface, and their behaviour is coordinated from a virtual sequence in a higher level env. So the virtual sequence here is coordinating or orchestrating the behaviour of the sequences on each of the individual agents. If we want to do end-to-end checking, then we might instantiate a scoreboard, another component within our verification environment, in which case the transactions being sent out from the monitors are being sent to a scoreboard, and the scoreboard can be looking at traffic that's coming from more than one agent. The env is then instantiated within a test, so the test forms the top-level class within our class-based verification environment. Of course, in the class-based world, when you create an instance of a class, that's known as an object. So each of the boxes on the diagram here correspond to objects in the object-oriented programming sense. So here we have an object hierarchy within our executing System Verilog program. Each object is of a specific class. Going back a step, one of the main purposes of UVM is to support constrained random verification. And if you remember, in constrained random verification, we're going to randomize some element of the stimulus that we inject into the design under test, which means as a result that the output from the design under test will also be randomized to some extent. And to make coverage-driven constrained random verification work, we need to use what I refer to as the 3 Cs. The first of the 3 Cs are checkers. Our verification environment needs to be self-checking. We need to insert assertions or checkers into our verification environment in order to assure ourselves that the design is functionally correct. The second of the 3 Cs is coverage, which includes code coverage and functional coverage. So into our constrained random verification environment, we're going to build functional coverage constructs that measure when we're done. And the third of the 3 Cs is constraints. So within our verification environment, we're going to be using constraints in order to shape the random stimulus that we inject into the design under test in order to make sure that we thoroughly exercise all the features in the design under test that we're interested in and that we measure in our functional coverage model. So now I'm going to relate these 3 Cs, checkers, coverage and constraints, to the UVM verification environment, and we'll see how it all fits together. So going back to this picture of a UVM verification environment, which, not by coincidence, is the sort of shape of the environment that we get generated from the easier UVM code generator, let's have a look at how everything fits together. So as I've already said, we have one agent per interface. Sequences will then run on sequences on that agent in order to generate stimulus. And if you're doing traditional constrained random verification, you're going to want the sequences running on the agents to do the heavy lifting of stimulus generation. So we have sequences here that are constrained in order to push the design under test into interesting states in order to ensure that we can maximize our functional coverage. Sequences then generate transactions. Transactions are themselves objects, and those transactions will contain the essential data needed to wiggle the pins on the design under test, as needed according to the specific protocol. So for example, if we're talking about a bus interface here, then the essential data in the transaction is likely to be data, address, and whether we're executing a write cycle or a read cycle on the bus. Plus maybe other data related to the protocol, such as priorities. Transactions might also contain metadata, data such as timestamps and IDs, in order to maximize the value of the verification environment. The driver gets transactions from the sequence running on the sequencer, and the driver then wiggles pins in the System Verilog interface instantiations, and the dashed lines here represent System Verilog virtual interfaces. So we'll have virtual interfaces within our UVM classes that refer to actual interface instances within the test harness. The monitor then looks at the pin wiggles, assembles transactions, and sends those transactions off for analysis. The connections here within the class-based verification environment are all transaction-level connections. UVM makes use of the TLM-1 standard that it borrowed from SystemC. So when we're passing transactions around within the UVM verification environment, we do that by passing transactions from TLM ports to TLM exports. In this particular case, we're making use of analysis ports and exports. Analysis ports and exports provide a broadcast mechanism so that a single port here on our monitor component can broadcast transactions to multiple subscribers. The first of the subscribers here might be doing functional coverage collection. So The agents represent a layer of components that are directly connected to the interfaces, and they deal with the nitty-gritty of pin wiggling. The agents understand specific protocols being used to communicate with the design under test. The agents are then sending transactions to higher layers in the UVM verification environment for analysis. So the subscriber might be doing functional coverage collection. The scoreboard, on the other hand, might be doing end-to-end checking. And you've got some discretion here. So there's no hard and fast rules. We could be doing checking and coverage in the subscribers, checking and coverage in the scoreboard. Then moving clockwise around the diagram, the virtual sequence is used to coordinate and control the behaviour of multiple agents. So we'd have a virtual sequence associated with this environment, and the virtual sequence may start the sequences running on the individual agents, and it's those sequences running on the individual agents that are doing most of the work of stimulus generation. The top-level verification environment is instantiated within a test. The test class itself may contain a relatively small amount of code. In essence, it's going to instantiate the environment and create any necessary tweaks to the environment. So a test might, for example, add a few extra constraints to a sequence in order to shape the stimulus that's being generated for the purposes of that particular test. UVM then provides a couple of ways in which we can customize the behavior or structure of the verification environment. And the first of those is the configuration. So configurations in UVM play exactly the same role as parameters in Verilog or generics in VHDL. In other words, you can use configurations to configure or parameterize the behavior or structure of the verification components. And with configurations, you have to anticipate in advance the kind of ways in which you're going to want to parameterize those verification components. So just as if you want to parameterize a Verilog module, you have to add parameters to the module as you write the module. So if you want to parameterize an agent with configurations, you have to access the data inside those configurations as you write the agent. Then, from your env or your top-level test, you can make configuration settings in lower-level components. So configuration information typically flows top-down through the UVM verification component hierarchy. So a top-level module or the top-level test might set configuration parameters that are then read by the env. The env may in turn set the configuration parameters that are used by the individual agents, and those configuration parameters might be used to switch in and out optional features, or to set the size of memories, or to start sequences, or constrain the behavior of existing sequences, or anything else that you might imagine. There's then a second mechanism that we can use to parameterize or customize the behavior or structure of the executing verification environment, and that's the factory. The UVM factory is a very flexible mechanism which, to cut a long story short, allows us to swap objects for other objects as the UVM verification environment is created or as it executes. So each time in UVM you create an object, and that could be an object such as an agent or a driver that's created at time 0, or it could be an object that's created dynamically during simulation, in particular sequences and transactions. Each time a sequence or a transaction or a component is instantiated in UVM, the factory comes into play. And factory overrides allow you to come along after the fact and replace the type of an object that's being instantiated with a different object type. So by setting factory overrides in a test or higher up in the verification environment, you can modify the actual behavior or structure of lower level components. For example, if you go out onto the web and buy some verification IP that's implemented in UVM, you might find that you have a bunch of agents and sequences that you take, instantiate within your env and then run. And if you want to modify the behavior or structure of the agent or the sequences, you can do that by extending the classes that represent those components or sequences, and then using factory overrides in the test by replacing the original classes with your new extended classes. And that's a key mechanism in UVM that allows verification component reuse. It really is very flexible. So in addition to the features that are highlighted on the diagram, there's a few other features it's not particularly easy to highlight on the diagram. So we have objections. Objections are the mechanism in UVM that used to determine when you get to the end of a test. If we want to be a bit more pedantic about it, an objection actually determines when we get to the end of a specific simulation phase, a phase such as resetting the DUT or running the main business of the sequences on the DUT. Then we have message reporting. So UVM has a standard way of reporting messages. And the register layer. I'll say more about the register layer in a few minutes. So those are some of the main features of a UVM verification environment. We can see that we use sequences for doing constrained random stimulus generation. We use subscriber components for functional coverage collection. And then we might do checking, either in a scoreboard for doing end-to-end checking, or we might build system Verilog assertions into our interfaces. If we move sideways a little bit and have a look at the easier UVM code generator, the code generator will of course generate this kind of structure based on a set of template files and include files that you provide. So the idea within the code generator is that you provide template files for each of your interfaces, and the code generator is going to generate the structure seen here for each of the interfaces. So the code generator will generate the agent, all of the components that comprise the agent, and a subscriber, and so on. You can then choose whether you want to have these agents instantiated within the top level env, or whether you want the agents to have their own envs. That's flexibility that you have when you set up the template files for the code generator. The code generator also generates for you example sequences. So the code generator will generate classes to represent the transactions, sequences and virtual sequences. And all of the sequences are started out of the box when you run the code that comes out of the code generator. So the code generator gives you a complete working UVM verification environment just to get you started. Well, I said earlier I'd say a few things about the register layer. So finally, let's mention the UVM register layer. The idea of the UVM register layer is to provide a layer of abstraction around the address map of all of the control and status registers within the design under test. So using the register layer, from your stimulus, you can simply read and write registers within the register model here by name without knowing the precise addresses of the registers in the register map. And the register model also abstracts you from the endianness of the interface, the specific protocols used to connect to the design and the test, and even abstracts tests from needing to know about whether the tests are being run at the block level, the subsystem level, or the full chip level. So the register layer works by instantiating a register model within the top-level verification environment. That register model would typically comprise many lines of code, and so in practice you're going to want to get hold of a register model generator. And all of the EDA vendors now will provide you with a register model generator. They might work in a proprietary way. A lot of them work by reading an IP exact description of all of the control and status registers in your design under test. If you're using the easier UVM code generator, that's going to instantiate the register model for you in the top-level env, also instantiate the necessary predictor and adapter components with each agent, and make all of the connections. So the beauty of using a code generator is that it can generate all the boring boilerplate code for you and connect everything up. The easier UVM code generator won't generate the register model for you, however. You'll be using a separate code generator for doing that. What then happens is that the virtual sequence within the top-level env will start a virtual sequence associated with a specific agent, and that virtual sequence can then make reads and writes into registers in the register model. The registers in the register model will then have been connected through an address map to the components in the UVM verification environment, such as the predictor, the adapter, and the sequences within the agents. So, I've shown you the big picture of what a UVM verification environment looks like. If you want to try all of this for yourself, you can get access to the easier UVM code lines and the code generator from the URL shown here. You'll be downloading the UVM code generator under an Apache 2.0 license, so the code is yours to do whatever you like with. You also have access to the easier UVM coding guidelines to do what you like with. So you can use the coding guidelines exactly as you find them, or you can pick and choose particular guidelines that you like and integrate them into your own specific UVM coding guidelines. At Doulos, we deliver training worldwide on the topics of hardware design and verification, system-level modelling, embedded systems, ARM processor technology, and also FPGA technology. So if you want to know more about Doulos training, visit our website www.doulos.com.